Hello, in today's video we are going to do an exercise where we will use some of Autodesk Inventor Professional 2021 simulation tools. We are going to design a Geneva wheel, type of mechanism, and simulate its movement. The objective is to get you familiar with the simulation environment. Let's start with the design. Let's create the sketch that is the base of the mechanism. To create a Geneva wheel, we start with a triangle. This leg of the triangle is the arm of the driving wheel, we can call it the crank wheel. This leg is the axis of the slot on the Geneva wheel. And the hypotenuse is the distance between centers of the wheels. We design the mechanism exactly when the crank pin enters the slot on the Geneva wheel. At this moment the crank arm is perpendicular to the slot. So this angle will always be 90 degrees. This angle by design will be 180 degrees divided by the number of slots. In the design is half of the advance of the Geneva wheel when the driving will do a full turn. For example, we will design a wheel that will advance 60 degrees per turn of the crank, therefore we need 6 slots. Then 180 divided by 6 is 30, which is half of the advance. Now, we can fix one of the dimensions of the mechanism. The others will be determined by it. We can design by entering the Geneva wheel radius. Or we can design by entering the crank wheel arm distance. Let's design it by entering the distance between centers, in this case 8 inches. As we can see, the others' dimensions cannot be changed, being determined by the distance between centers. Let's draw now the driving pin. For diameter we can do 3/4 of an inch, just a proportional dimension, without any calculation for this example. This is the circle that the pin will travel. By putting a pin here, we can see how close it gets to the center of the Geneva wheel when it rotates. This is the outer diameter of the Geneva wheel. If we transfer this radial dimension, we can determine the bottom of the slot. A prominent characteristic of the Geneva wheel mechanism is that it stays locked when it is not rotating. This is achieved in different ways, but commonly it is held with a shoulder on the crank wheel. Let's place a circle here, let's dimension it arbitrarily, just proportion. This is the shoulder on the crank wheel, and a mating cut has to be done on the Geneva wheel as many times as it stops. Let's do a circular array of the slot and the stop profile to create the wheel. We select the part of the sketch we want to repeat. Then we select the center of the circular array. In this case it has the right amount, 6. We can use this sketch to extrude the Geneva wheel. Let's leave it at 1 inch as distance for the thickness. As I said, it is a representational example, without dynamic calculations. Let's save the part. If we go back to the sketch, we can see the design dimensions for the crank. We can share this sketch and extrude it from it, or we start a fresh new part knowing the dimensions. We know that the pin diameter is 3/4, the rotation radius is 4 inches and the locking shoulder is 6 inches in diameter. So let's create a new part. There are many ways to design the crank wheel. I'm just going to model a common one in the shape of a disc. The diameter of it has to be larger than the rotation circle of the pin to be able to place it on it. The pin rotates in a circle of 8 inches, plus the pin diameter, it equal to 8.75, so we are going to make a disc of 10 inches. Let's extrude it arbitrarily 1 inch in thickness. Let's sketch the pin. Here we don't have to draw the pin at any angle, it is the same all around the wheel. I'm doing it so it has more resemblance to the sketch we use for the design, but we don't have to. The radius is 4 and diameter 0.75 inches. Let's extrude the pin 1 inch as the Geneva wheel. Let's create now the locking shoulder. In the locking shoulder, we have to make a cut for clearance when the Geneva wheel is moving. Its diameter has to be larger than the outer diameter of the Geneva wheel. Now we have the crank wheel. Let's add an axle behind for ease on the assembly. Any proportional dimension, it is only a representation. Let's save it. Let's create a housing for the mechanism. Anything that keeps this two wheels apart 8 inches and in the same plane will work. I'm going to create a more elaborate one, just for aesthetic purposes, but we don't have to. Let's save it. We have to add a shoulder behind the Geneva wheel, so it ends at the same plane of the pin and above the crank disc. Any diameter as long as it does not interfere with the disc. Let's extrude at the same thickness as the crank disc. Let's add an axle. Let's start an assembly. Let's place a component, first the housing. Right-click and select Grounded. Let's place another component, in this case the Geneva wheel. Let's apply constraints until the only degree of freedom left is rotating. Let's place now the crank. We are going to constrain it the same way. Let's change the visual style to shaded with edges, to see better. Before a simulation, I like to arrange the components as close as I can to the right position. It makes it easy for the computation. To start a simulation, we click on Environments, then on Dynamic Simulation. The first thing I do is to check which components are grounded and which are mobile. As we can see, the Geneva wheel is in the wrong group. It took it as grounded, but it is not. To fix it, right-click and select Retain Degrees of Freedom, which will bring it back to how we constrained it in the assembly. As we can see, it moved to the mobile group. The constraints we placed on the assembly left 1 degree of freedom for the Geneva and crank wheel, only rotation. On the simulation environment, it is translated to a revolution joint. We could have obtained the same by adding revolutions joint between the wheels and the housing. A joint is a set of constraints. Now let's add a force joint. "3D contact." This is a very interesting joint. It makes the pair of objects behave like real-life solid pieces. In it we can set all the properties, like friction, stiffness, etc. It makes the contact of the pair very real. In our case, we are not going to set any of this parameters. Like I said before, this exercise is just a representation of the movement, and we are not getting into the dynamics of it. Select the first object, and the second. Let's getting the crank rotating. We right-click on its revolution, and select Properties. A window appears where we can change the properties of this revolution. Let's click on the Degree of Freedom tab. Here we can have many options to alter the behavior of the joint, making it closer to real objects. We can get it moving by adding a torque, but this is not how we are going to do it. We are just going to impose a rotation to it. This makes it very simple. It will start at 0 degree and end at 360 degrees in 3 seconds, a revolution in 3 seconds. Let's change the simulation player time to 3 seconds too. Press play, and here we have our first revolution. If we press repeat, It will look like it is rotating continuously. Let's play with the visual style. Let's stop the simulation to modify the mechanism. We are going to change the crank wheel. So right-click, and select Open. We are going to add another pin, diametrically opposite. First we are going to extrude cut the clearance for the Geneva wheel. So 8 inches center to center, and 14 inches in diameter. Now let's do the sketch for the pin. Three-quarters of an inch in diameter and the same height. Save the changes. Back in the assembly simulation environment. To be sure it will work, I will delete the previous 3D contact and add it again. Trying to run the simulation, we found an issue. Let's take a look. As we can see, it moved the crank wheel to the grounded group. So right-click and select Retain Degrees of Freedom. Now it is back into the mobile group and with a rotation joint. Let's impose the move. This time it will rotate faster, 360 degrees in 2 seconds. We have the rotation, but it doesn't seems right when we click repeat. The problem lays in the time of the simulation player. It has to be the same as the rotation if we want to use repeat. Bear in mind that to achieve continuous movement we do not have to use repeat. If I would have used a torque to move the crank wheel, or I would have simple move at a larger amount of degrees than 1 revolution, it would have rotated several times without the need to repeat the movement. Here we have the output grapher window. This is an amazing tool. We can see and gather all the kinematic and dynamic resulting data from the event we created. On the top space we find the data in numerical columns. On the lower part we have a graphical output. This is what we are going to use. Let's take a look at the Geneva wheel angular speed. We go to its revolution joint and expand all the parameters being measured. Go to velocities and check on V1. As we can see, we have a curve representing its behavior. So first the speed is 0, then it accelerates until reaches 180 degrees per second, then to acceleration to the intermittent stop. It is just negative because of the direction of rotation. Let's fix it. Let's change the sign of the angular displacement. Let's try again. Now looks better. Let's check if the max angular speed of 180 degrees is correct. Let's take a look at the original design sketch. This is the trajectory of the pin, pushing the Geneva wheel. The arm of the crank is 4 inches, and the Geneva wheel arm is 4 inches at this point too. The angular speed of the Geneva wheel is 0, when the pin enters in contact, then accelerates to maximum speed at this center point, and starts to accelerating to 0 again. Since the arms are the same at the center point, the maximum speed of the Geneva wheel will be the angular speed of the crank wheel. Let's go back to the simulation. Let's see the graph. We have 0 velocity, the 180 degrees per second, and again 0. As we can see, the crank wheel is rotating at 180 degrees per second. The pin enters, accelerates the Geneva wheel, and then decelerates to 0 velocity. Let's see it again. Let's change the angular velocity, 360 degrees in 1 second. Let's run it again. The problem here is that the simulation player is still running for 2 seconds. Let's fix it. As we can see, the Geneva wheel maximum velocity is equal to the crank wheel velocity, 360 degrees per second. This is an introductory video to get you acquainted with mechanism simulations of Autodesk Inventor 2021. Working with the program, investigating new ways to do it tasks and consulting the software help, will develop further your skills. Thanks for watching. I hope you found this video instructive. If you like this video, make sure to subscribe for more.